This is Stanford Engineering's The Future of Everything, and I'm your host, Russ Altman. If you enjoy the podcast, please follow or subscribe wherever you listen to your podcasts. It'll help us grow, and it'll make sure that you never miss an episode. Today, Monika Schleier-Smith will tell us about quantum mechanics and a mysterious and amazing phenomenon called entanglement. It's the future of quantum mechanics. Before we jump into this episode, I'd like to ask you to rate and review the podcast. It will help us improve, and it'll make sure that others learn about the podcast as well. So, there's physics. In the old days, we had classical physics where there were particles. Particles had locations, they could move, and they would have momentum and velocity, and we could measure all of those things. And that was all true until the beginning of the 20th century, when physicists were compelled to invent quantum mechanics, which is a much more complex version of physics that is necessary to understand and explain the behavior of atoms. Quantum mechanics is filled with non-intuitive phenomenon. For example, sometimes you can't measure both where a particle is as well as how fast it's moving. Sometimes two particles can talk to one another at a distance through unclear mechanisms. Well, Monika Schleier-Smith is a professor of physics at Stanford University, and her lab studies quantum mechanical phenomenon, especially this amazing phenomenon of entanglement. In entanglement, two atoms seem to be talking to one another and doing things in a correlated manner with no clear physical connection. Well, that's not right. Actually, the physical connection is through quantum mechanics. Monika Schleier-Smith will help us understand a little bit about how to think about entanglement, how to measure it, and how to make sure that you can get your molecules into an entangled state and make sure that they stay entangled. So Monika, many people don't think about quantum mechanics and quantum systems every day. So I think it's important to start out for you to explain the key features of quantum mechanics and what makes it so fascinating to study to you.
Sure. Well, the reason many of us don't think about quantum mechanics every day is that it's not a natural sort of theory to describe our interactions with the everyday world. It describes really kind of microscopic systems, atoms, electrons, and their behavior. And it has a number of kind of really remarkable features that seem counterintuitive to sort of based on our everyday lives, such as quantum uncertainty.
Yes.
This is something sort of that first got me interested in quantum mechanics. I learned in my high school chemistry classes that if I think about an electron, I shouldn't think of it as just being at a point with a well-defined position and a perfectly defined speed, but actually there's some fundamental uncertainty in where it is. I should think of it as kind of smeared out in space, and I can never know precisely where it is and how fast it's moving at the same time.
And that's quantum uncertainty, and that's a real thing for like all particles, basically.
That's right. Yeah, that's right. And that tells us more generally that whenever we kind of measure the properties of a particle, there's some kind of random probabilistic aspect of it. We can measure the position of an electron, but we fundamentally can't predict from the outset what the result of that measurement is going to be. So quantum mechanics, the laws of quantum mechanics are probabilistic, and that sort of blew 20th century physicists' minds. We always previously thought that the laws of nature are deterministic.
Right.
But beyond that, there are remarkable properties such as, really, I would say the most remarkable feature of quantum mechanics is something called entanglement, which says...
which is I just have to say, it is a great word. Whoever was the physicist doing marketing picked because entanglement, we kind of have a sense of what it might be, but we don't really, so please continue. I just got to say, it's a great word.
Yeah, so I mean, entanglement essentially tells us that tells us something fundamental about information in our universe, that information doesn't have to be stored locally in something like a single bit in your computer or a single particle, but rather information can be non-local and can be somehow shared or distributed between particles. And that can show up in funny ways where if I measure the state of one electron, it looks random, and I measure the state of another electron, and it looks random. But if I were to compare the measurement outcomes, I would always see some correlations in the randomness.
So that's really, just to stop there for a minute, that means that even though they look random, something is being transferred between them to allow them to be correlated, right? They must be getting information from one another in some way. Is that true?
Well, I would be a little bit careful and say something has been transferred between them. So, and so, I mean, the type of, I like to sort of use an analogy. It's as if I were here in my office tossing coins and you were in your office tossing coins. And if we, didn't compare notes, it would look totally, both coin tosses would look random. But we could have a situation where I toss my coin 100 times, and every time I get heads, you get heads. And every time I get tails, you get tails. And that's weird, right? That would never actually happen. And that could happen. You're probably in another office at Stanford, I'm not sure, but even if you're somewhere else in the world, like in principle, this can happen over very long distances.
That's the other thing. So the entanglement literally is that they're kind of, there's an interaction between them that kind of tangles their futures or their present
Exactly. And so initially there needs to be some interaction that establishes that entanglement. And that allows subsequently these two particles to be correlated. So it's not a way to transmit information faster than the speed of light. It doesn't break that law.
So do these particles generally need to be close to one another at some point in order to establish that relationship, and then they can travel far apart? Or can that establish? And I understand this is probabilistic, but in general, are the most probable entangled atoms the ones that have been close to one another, or is that not even true?
So in general, intuitively, you would think they should be close to each other to establish that entanglement. And it's true that at some stage, that's required, some kind of a local interaction. But so if, for example, I can take light or photons, particles of light, and those can sort of easily travel over long distances. And so those could then be used as sort of a messenger to generate entanglement between some systems that are further apart.
And what is the time persistence of these phenomena? So like, I know that if you and I talk and say, we're going to do a dance, but we're not going to look at each other, we'll start off looking pretty correlated, but unless we are really good timing, my dance is going to start to look different from your dance after a couple of minutes. So is there a similar phenomenon with this entanglement where as time goes on, the kind of level of communication or correlation degrades?
Yes, absolutely. And in general, this is kind of, I would say, one of the big challenges in kind of harnessing this phenomenon of entanglement for a variety of technologies where it's useful, is that it is difficult to preserve. And it's maybe not so surprising because essentially this other sort of remarkable aspect of quantum mechanics is that when we measure a quantum system, it has to sort of, initially it has some inherent uncertainty, but it has to decide when we do a measurement. Right. And so that process of that measurement actually affects the quantum state, and it can destroy the entanglement. So if initially, you and I each had a particle and they were in an entangled state, but I measure mine, then after that, this sort of entanglement, this state has collapsed, one could say, into a particular configuration. Like after I measure my coin to be heads, we know that yours is also heads, and from that point on, the randomness is gone. If we do another measurement, we'll actually get the same result. Wow. And so because the measurement necessarily perturbs the quantum state, that means that could be something that we intentionally do, that I intentionally, measure the state of my electron, but it could also be something that happens unintentionally. Some light bounces off this system that I'm trying to preserve in a fragile, entangled state, and just that photon bouncing off of my atom, let's say, perturbs its state, and now that can destroy the entanglement, even if I don't look at the measurement outcome. Got it. Okay. But in terms of absolute timescales, I would say it depends a lot on the physical system. It might be nanoseconds, it might be seconds, and now it depends on the... Okay, so that's very helpful. So, and we started this part of the conversation where you're saying that this is one of the things that gets you find the most fascinating in quantum mechanics is this entanglement phenomenon. And I believe you study it. And so maybe you can tell us, and it sounds like you've implied for sure that you've been able to create some entangled atoms. And it sounds like from your most recent comment that sometimes you work very hard and that other things are kind of messing up these systems that you've worked
very hard. So tell us what happens in the lab and how do we actually study this? And then later on, we'll talk about what are the applications that might come out of this downstream.
Sure. Yeah. So, there are a variety of physical systems where this has by now been studied, but the platform we work with in my lab is one of laser-cooled atoms.
Okay.
And so maybe I should kind of break that down a little bit and say that.
Yeah, I think of lasers as heating things up. So right away, I'm a little bit confused.
Exactly. Yeah. So, and so first of all, what do I even mean by cold? The idea, their goal is to have kind of atoms that are very well controlled, that aren't just whizzing around as they are at room temperature, but that are essentially brought to a standstill and kind of held in place in a vacuum chamber where there's no other atoms colliding with them.
Okay.
The lasers are essentially a trick for getting those well-controlled atoms. And like you said, you might think a laser should heat things up. But it turns out there's a trick to use a laser to slow down atoms if I use basically a laser with a very specific wavelength that interacts with a particular transition. Let's say one of the atoms we use is rubidium. Rubidium has a transition at 780 nanometers, and if I have a laser that's exactly at the right wavelength, it can be used to very precisely control that atom.
Okay.
Should I say a little bit about the trick for cooling them down?
What the heck? Absolutely. This is a podcast where time is a very ephemeral concept. So yes, please tell us about that.
Yeah. So there's a trick that involves the Doppler effect.
Okay.
And the way you can kind of visualize it is, imagine I have an atom that's sort of whizzing around in my vacuum chamber, and I have a pair of laser beams. We'll actually do this in all 3 dimensions, but let's think about a pair of laser beams that's sort of counter-propagating.
Yes.
And what we do is we tune the lasers so that they're a little bit lower in energy than what they would need to be resonant with the atomic transition.
Right. So you gave me a number before. You're going to be close to that number, but not the same number. 700,
yeah, exactly.
780.
At some far out decimal point will be a little bit less than that number. And so a little bit, lower in frequency.
Yep.
And now the Doppler effect is going to help us. So, this phenomenon where basically like I'm driving along and there's a truck coming the other way. And if it's coming the other way, it'll sound kind of higher pitched.
I live next door to the train tracks here, and in fact, I go on mute sometimes when we're talking so that you don't hear them. But it is nothing but Doppler effect all morning.
Right. So that same effect means that this atom that's whizzing around, if it is moving sort of opposite the direction of a laser beam, that laser beam, it'll sound like it'll seem like it has a higher frequency to the atom.
And it gets you into that magic zone.
Normally it wouldn't be resonant, it becomes resonant.
Yes.
The other laser beam is sort of pushed away from resonance. But the key point is the laser beam that's pointing opposite the atom's motion, that's the one that we want it to interact with, because it's going to give it a kick. That photon is going to give it a kick that slows it down.
And just to make forgive this very primitive analogy, but if I have a train coming towards me and if it sounds like an A flat note, if I run fast enough towards that train, I could increase that A flat to a normal A by the Doppler effect. And then if that A leads to me being entrapped, or whatever the right word is, then now that train is controlling me where it couldn't control me before, but I ran fast enough to hit that magical frequency.
Exactly. Okay. Yeah, I have this picture in mind now where once it hits an A, some wine glass starts.
Exactly. Some beautiful thing happens. Okay. So that was great.
We just want to slow down. We just want to give this atom a little kick that slows it down.
So once you've isolated these atoms, my guess is you have to get 2 of them or something to do this entanglement trick. But please go on about entanglement.
Yeah, exactly. So slowing them down, that's just the first step. And then we trap them. You can also sort of trap them at the focus of a laser beam. And, there's some labs, a number of labs around the world where people have actually individual atoms, E1 trapped at the focus of each laser beam. That's not exactly what we've been doing so far in my lab. We have maybe some clouds of thousands of atoms at the focus of each laser beam. But, the details might differ from one experiment to the next. But roughly speaking, we have these atoms, we trap them, and now we want to actually get them to talk to each other to generate this phenomenon of entanglement.
So how do we do that? Because now I'm all on board with this.
Exactly. And so there are actually a few different tricks you can use. One is, you said before, maybe they should be close together if you want them to talk to each other. So what you mean by close together, might depend on what system you're used to thinking about. In a solid, the atoms are separated by kind of angstrom scales. In these systems where we use light to manipulate atoms, the kind of characteristic length scale on which we can control their motion is the micron scale, roughly the kind of wavelength scale.
Right. So a micron, for people who don't think about microns, there's a million of them in a meter.
Yeah. If you want to get interactions on the micron scale, one trick that you can play, and this is something we've done in our lab, is take an atom and excite it so that the electron cloud becomes sort of bigger and fuzzier. So you can excite the electron to something called a Rydberg state. And then actually atoms that, again, a micron is way further apart than atoms would be in a solid.
Right.
But even on that length scale, they can start to interact and become entangled. That's one approach. Yep. But another approach we take that sort of blows up the length scale even more, if we want to get interactions on the millimeter length scale, then we can play a trick where we use light to convey information between different atoms.
Yes, you hinted at that earlier. I noticed you were talking about light as a messenger.
Yeah, exactly. And so, and that can happen on length scales of kilometers, but then you start to have less control.
And also your lab would have to be very large, and I'm sure the dean would be upset.
So there are some trade-offs depending what distance you're aiming for, but we can have sort of a millimeter scale system, atoms that are millimeters apart, and trap them between two mirrors. That forms an optical resonator or cavity. And light, basically, the point is, if the mirrors are good, then light can make many, many round trips, thousands or even 100,000 round trips between the mirrors before it leaves. And that actually gives a way for the light to kind of carry information between these atoms and let them talk to each other kind of secretly without that information leaking into the outside world. Because if it were to leak to the outside world, in principle, somebody could measure it, and that could destroy this entanglement.
Gotcha. Now, one final question before we go to a break, which is when you've done all these, you mentioned 2 or 3 manipulations that can get these atoms entangled. How do you know that they're entangled? What's the assay or the test where you all shake each other's hands and have a party and say these atoms are definitely entangled?
Right. So in general, this is a great question. Because what you need to be careful about is that you're not just seeing some classical correlation,
right?
And that there's really sort of no way. You see these correlations, but you need to really prove there's no way that information, sort of in principle, even could have been known in advance. And so, actually, there's a wonderful, just as a digression, there's this wonderful paper by the theorist John Bell, who had sort of seminal contributions to how you prove entanglement. Huh. And it's called Bertelsmann's Socks and the Nature of Reality. And it describes a Professor Bertelsmann, who sort of, if you see his right sock on any given day and it's blue, you know that the left sock is not going to be blue because he always wears mismatched socks, right? And it's random, sometimes they'll be blue, sometimes the first one will be red, but they won't match. Okay, so that's not entanglement, but it seems kind of similar, right? Like if when it's blue, the other will be red.
That's what you referred to as classical correlation.
That's what I mean by classical correlation, exactly. And so generally, to prove entanglement, you somehow need to do measurements of two fundamentally kind of incompatible observables. So earlier I talked about like the position and the momentum of a particle, and one can essentially prove that you can't know both of those to arbitrary precision. With entanglement, you could set up a system where if I measure the position of one particle, it's perfectly correlated with the momentum of the other. And if I measure the If I measure the position of one particle, it's perfectly correlated with the position of the other. If I measure the momentum of one particle, it's perfectly correlated with the momentum of another. And so using the information in one particle, you can perfectly predict either one of these two kind of incompatible observables in the other particle. And that's one example of how one can prove entanglement. And this is something we've done kind of variants of this in our quantum systems of atoms in the lab. In our case, we're not working with position and momentum. It's something like the atom has some kind of a a spin that can point anywhere on a sphere, and there's no way you can measure both in the up-down direction and the left-right direction at the same time.
Is it true? So you mentioned before something about measurement affecting the system, and therefore you really have to budget your measurements very carefully. When you do this measurement, is it going to ruin the entanglement, or do the molecules or the atoms live on to continue to be entangled, or is it a destructive measurement?
In our recent experiments, we've been doing destructive measurements.
Okay.
There's also a class of measurements called quantum non-demolition measurements.
Non-demolition.
Where this is actually kind of if you read a textbook on quantum mechanics, it will tell you after the measurement, the system is in the state that corresponds to the measurement outcome. Often that's not true.
Okay.
Like I detect a photon, the photon crashes into the detector and the photon is gone.
Okay.
There is this special class of non-demolition measurements that can actually be used to generate entanglement. You look at the measurement outcome, and the measurement outcome tells you something like if this electron was moving this way, the other one had to be moving the other way because I measured that their total momentum was 0 or something like that.
Okay, right? Very good.
Just conceptually. So yeah.
This is The Future of Everything with Russ Altman. More with Monika Schleier-Smith next. Welcome back to The Future of Everything. I'm Russ Altman, and I'm speaking with Monika Schleier-Smith, a professor of physics at Stanford University. In the last segment, Monika told us about quantum mechanics and especially about this fascinating phenomenon called entanglement, how you can get atoms to be entangled with one another, and how you can make sure that they're entangled. In the next segment, Monika will tell us some of the applications of entanglement once we can control it. This has wide-ranging implications for very accurate clocks, sensing, communications, and even quantum computers. So Monika, I wanted to ask you now about the downstream applications if you're successful at routinely being able to create entangled atoms, make sure they're entangled. What are the kinds of things we're going to be able to use that for?
Yeah, so broadly speaking, there are kind of a few different spheres of application. One is precision measurement. So I mentioned to you that there's some kind of randomness inherent in quantum mechanics, some probabilistic nature. That can actually limit the precision of things like clocks and magnetometers, accelerometers, and entanglement can be a resource for actually getting to even more fundamental limits of precision. Another really exciting potential direction is computation, and that's one that you might have heard about.
Yes, these are the so-called quantum computers that I've been basically waiting for my entire professional career.
Right. Yeah, and so, you've been waiting a while, but I would say there's been actually really a lot of progress in just the past sort of decade or two or so in the level of control we have over entanglement and the ability to kind of not only entangle two particles, but scale that up to more in order to approach this vision of quantum.
Oh, this is a very important question. Let me interrupt you. Yeah, we've been talking about two atoms being entangled. Can it be a threesome or a foursome where there are three or four, or is it always a pairwise phenomenon?
Yeah, so there's actually a sort of a rule called monogamy of entanglement.
That's exactly what I was wondering about.
But you can have either two atoms, let's say, or two particles that are maximally entangled, or you can have many atoms that are weakly entangled, where there's a little bit of entanglement between each pair. And actually, some of the states we've been creating in my lab, which are partly motivated by these sort of improving precision measurements, they actually feature this sort of phenomenon where there's maybe 1,000 atoms and there's sort of weak correlations between different pairs of those.
Okay, thank you. I'm sorry that I interrupted you. You were talking about quantum computation.
Sure. Yeah. I mean, so that's another exciting application. And maybe just to mention sort of one third one, quantum communications is another direction. Can you sort of leverage entanglement and the fact that it can exist over long distances to really kind of securely have secure communications where the laws of quantum mechanics kind of prohibit eavesdropping. Right. So those are kind of three spheres of application that are kind of.
So why don't you pick one and take us through how the kind of features that you've described for entanglement would enable. It actually almost doesn't matter. You talked about censoring, computation, other things, communications. Take us through how the entanglement. I think people would be interested in. Is this going to be Is this going to be very power hungry, or does it have a possibility of being very green and efficient, and also things like precision and speed? I think people care about as well.
Yeah. So Yeah, so just to give a couple of examples, maybe I'll give some examples from the sensing and the computation area.
Great.
So in sensing, again, it's essentially, so one of the places where specifically the systems I talked about, these laser-cooled atoms are used, are in atomic clocks, which are our best measurements of time. The second is defined in terms of some number of oscillations in a cesium atom. And the best of these clocks, actually, it's remarkable. If you'd started one when the universe began, it would be off by some fraction of a second today. So they're really extraordinary devices already as they are. But the limitation actually in the best of these clocks is actually this randomness of quantum mechanics.
Yes.
The fact that somehow I need to measure whether an atom is in one of two states and there's some randomness in that outcome. So it turns out with entanglement, you can have this phenomenon where, let's say I have these two atomic states, the up state and the down state. It's a little bit like the heads and the tails of the coin. If I measure 100 atoms, I'll typically get some fluctuations on the order of plus or minus 10. But now with entanglement, you can set up this situation where if I measure one atom to be up, another one is more likely to be down. And that can actually reduce those fluctuations. So it can reduce those statistical fluctuations in the measurement, and that can enable a more precise clock. And clocks, in turn, have a number of applications, for example, in navigation, GPS satellites depend on clocks. And so this is something where it's exciting to be able to really sort of push the fundamental limits of what precision you can get leveraging quantum mechanics.
Yeah, so that actually is a great example, because I do know a little bit about the cesium oscillations, and they are always out to many significant digits. I think your point is that there are more significant digits to be had if we can remove the noise, and by having a number of atoms that are linked, you can kind of average out their errors. I mean, that's my phrase, not yours, to kind of get increased accuracy of the measurement.
That's right. You can get increased accuracy. You can also get the same accuracy faster, or the same precision faster, which can also matter. Some of these clocks are so precise they can measure how high up they are in a gravitational field.
Right.
A few centimeters difference will matter. And so then you can start to think of the clock as a sensor, and the faster it is, the better, right? And so, yeah.
What about computation? Because we do hear about breakthroughs. We know that some of the big tech companies have big investments in quantum computing because they obviously see an upside with success. So maybe take us through what the value proposition is of quantum computing.
Yeah. So just at a kind of fundamental level, this entanglement means that information can be stored not just in individual bits, but in correlations between quantum bits or qubits. And that means actually that because I need to keep track of not just the state of each bit, but all the correlations of if this one is more likely to be a 1, this other one is more likely to be a 0, the description of a system of n quantum bits takes resources classically that grows exponentially with n. And so if I just get to something on the order of 60 qubits, I cannot describe that system on even the world's largest supercomputer. And so that already kind of tells you that fundamentally these qubits should have some computational power that classical computers don't.
I see. That's interesting. So the proof is because our current computers can't even model it, it must be capable of doing things that our current computers can't do. Exactly.
And so there's one space of applications where the goal is to solve a problem that's inherently quantum mechanical, right? So chemistry problems that involve the quantum mechanics of many interacting electrons. Those are hard to do on classical computers. If you can do them better, that could have implications for, let's say, drug discovery, right? And so that's something where it's really natural to say, why don't we make the hardware natively be quantum mechanical?
Right.
Also problems in material science. And this actually, there's a bit of a gradient from computation to also something we call quantum simulation. Can you build model systems where the components are quantum mechanical, but you can maybe model the properties of the fundament, build a simple model that might capture some properties of, let's say, superconductivity.
Yes.
And so you could ask, can I build a universal quantum computer that can answer any problem, or you can have something more purpose-built to tackle a particular type of problem, like simulating solid-state systems to learn about superconductivity.
When I look at these papers, one of the things I'm struck by in addition to my not fully understanding the paper. But one of the things I'm struck by is that I don't have a good feel for the potential computational power of 60 qubits. You said 60 qubits is very hard to model. Would 60 qubits be a very non-trivial computer, or are we going to need to wait for the Moore's law of quantum computing to get us to millions or trillions of qubits in order to do really kind of non-trivial things?
Yeah, great question. So at the level of 60, you can start to get into this regime where you can't calculate classically what will happen,
right,
or it would take an unreasonable amount of time. But so far, we're not quite at the point yet of being able to actually like solve a useful problem with those systems. And then I would say there's sort of like two types of algorithms that people are working on. One is what's called, there's a term NISQ, which stands for Noisy Intermediate Scale Quantum Algorithm. So the question is, if you have some modest number of qubits in this regime, hundreds, where you can't have a full description on the classical computer, can you already start, and maybe they're not perfect, we try really hard,
right.
The gates might have 99.9% fidelity, but it's not 100.
Right. You told us about those nasty photons that can mess up your measurement.
Exactly. Can you use that already to start solving some problems? And so the flavor of problems there might be there are certain optimization problems, scheduling problems that you can actually map to minimizing the energy of some interacting system of spins, let's say.
Right.
So, and if you can program in the interactions, maybe you can sort of directly kind of take your problem, map it onto the hardware, and use the hardware to help solve it. And there's really an open question about to what extent quantum systems actually provide an advantage for this class of problem. It's, to the best of our understanding, if they do, it's probably something that's a polynomial win and not an exponential win. But I would say, there's a lot of good science in actually just building the systems and starting to explore and seeing how much they can help in that regime.
Great.
If you want to, but then there's this goal of having a full error-corrected quantum computer. And error correction is subtle in quantum mechanics because it's not enough to say is the qubit in a 0 state or a 1 state. It can be in this sort of so-called superposition of both. Where
yes.
So quantum error correction is another really active area of research, and having an error-corrected quantum computer will require many physical qubits for each logical qubit, and then the number that you need is going to be, not just hundreds, but hundreds of thousands.
Yes, I mean, I don't know if this is the right analogy, but even in your description of sensing, I could see that you were talking about multiple entangled things to kind of do an averaging, and I can imagine that to get an error-corrected computer that's quantum, you would also need to have a certain redundancy so that there could be like voting mechanisms and stuff where all the qubits get a vote to figure out if it's up or down or whatever.
Right, and the thing is, in quantum mechanics, you have to vote about is it up or down, but you also have to vote about is it left or right.
Right.
And
right.
So there's some extra subtleties there.
Well, very good. Well, thanks to Monika Schleier-Smith. That was the future of quantum mechanics. You have been listening to The Future of Everything, and I'm your host, Russ Altman. If you enjoy the podcast, please follow or subscribe it wherever you listen to your podcasts. Please rate and review it for sure, so we can grow our audience and so we can improve. We have a back catalog of more than 200 episodes, and you might want to look back at some of those because they're still the future of lots of things. You can connect with me on Twitter at @RBAltman or on Threads at RussBAltman, and you can follow Stanford Engineering at StanfordENG.